Let's look at some different types of inflection points. Let's suppose we have our objective function, y equals some function of x, in our top graph. Here's x, here's y. And when we graph out y is equal to some function of x, it looks something like this. And below it, we want to graph out that function's derivative function. So here's our function y equals some function of x. And the derivative function for different values of x, we want to graph out the derivative of our original function. So if you look at this function, y equals f of x, for these low values of x, as x increases from left to right, the slope of the function increases, which means the derivative dy dx increases. And it gets to some point here, and then beyond that point, if x continues to increase, the slope starts to diminish. So let's call this value of x maybe x1. And so to the left of x1, as x increases, the slope increases, the derivative dy dx increases. It reaches some maximum when x is x1. And beyond x equal to x1, if you keep on increasing x from left to right, the slope of the function starts to diminish, which means the derivative dy dx starts to decrease. So here's the graph of our derivative function of our original function, y equal f of x. Y is this point A on the original function. What makes it an inflection point? Well, what makes point A an inflection point on our original function is that at the same value of x, the derivative function, in this case, reaches a maximum. What would be an economic example of this? Suppose x were L, the amount of labor used by the firm, and our dependent variable y is Q, which represents quantity of output produced by the firm. So this function, y equals f of x, would represent the firm's short-run production function, expressed as Q is equal to some function of L. And it's a short-run production function because we only have one variable input, labor, and we're assuming the other variable input, capital, is fixed. So let's see here. In this case, on the bottom graph, x would be L, and the derivative dy dx would be the derivative of Q with respect to L on the vertical axis. And that represents the change in output or the additional output when the firm hires one more worker, and that represents the marginal product of labor to the firm. So this is simply the firm's marginal product of labor curve. And this derivative dq dl is the firm's marginal product of labor curve. So we could say the following. When the firm is using that amount of labor, for which the marginal product of labor is at a maximum, we have an inflection point on the firm's short-run production function. Let me give you one more example of an inflection point. Suppose we have our function y equals some function of x, and maybe it looks something like this. Here's y equals some function of x, and we want to graph out that function's derivative function in the graph below, dy dx. So if we start at x equals 0 and then increase x from left to right, you see that the slope of this function starts to go down, which means the derivative dy dx decreases. And that happens until we get to some point A at some value of x, call it x2. And if x continues to increase past x2, then the slope of the function, the derivative of the function dy dx, starts to increase. So again, remember, the derivative decreases, reaches some minimum value, and as x increases beyond x2, the slope of the function increases, the derivative dy dx starts to increase. So here's our graph of our derivative function. So what makes point A on the original function an inflection point? Well, at the same value of x, the derivative function, in this case dy dx, reaches a minimum. What would be an economic example of this? Suppose x represents quantity of output produced by the firm per year, per week, or something like that, and y represents the cost of the firm from producing these different output levels. So our function here would be a cost function. Our dependent variable y is c, which is a function of q. Cost depends on a function, or it's a function of how much output is produced. So if we look at this derivative function, again, x represents q, quantity of output produced by the firm. What is dy dx, or the derivative of c with respect to q? Well, what is the economic interpretation of that? What is the change in cost of the firm as the firm produces one more unit of output? What is the additional cost from producing one more unit of output? That represents marginal cost to the firm, marginal cost of production or marginal cost of producing output. And it's the familiar U-shaped marginal cost curve that you've seen in some of your microeconomics courses. So we could say the following. When the firm is producing that amount of output, at which marginal cost is at a minimum, then the firm is experiencing an inflection point on its cost function.